5.2, probability rules. And yes, probability does indeed rule. So we've previously used simulations to imitate chance behavior and get our estimates for probability, but those are just estimates. So we can actually calculate the exact probabilities, the true probabilities of outcomes, once we know some of the rules and how to calculate these things. So the first definition here in the green box, a sample space S, capital S, of a chance process is the set of all outcomes. So everything that can possibly occur, that's the sample space S. And then a probability model is a description of some chance process that consists of two parts. First part, it's got to have a sample space, capital S, so that's the set of all possible outcomes. And the second piece it has to have for a probability model is a probability for each event. So it has a sample space and it has a probability for each event within the sample space. So we've got a probability model that has two criteria, and then we have a sample space. So two new definitions or vocab terms to add. So the first example talks about rolling two dice, and mine's in color, so I have looks like an orange and then there's a light blue color here. How many outcomes are possible within this sample space? So if you roll two dice, what are the total number of outcomes, possible outcomes? And this is actually 6 by 6 here, so there's 36 possible outcomes in the sample space. So 36 different outcomes for S. What's the probability for each specific outcome? Well, none of these outcomes are more likely than the other. So it would just be 1 out of 36 for each one. So each outcome has an equally likely chance of occurring. So it's probability 1 out of 36 for all outcomes. The next note here, a probability model allows us to find the probability of any collection of outcomes. So any type of outcome that could occur within this sample space. That's what probability outcomes allow us to find. So let me scroll down here just a bit. The next green box here, the definition of an event. So an event is any collection of outcomes from some chance process. And we say it's a subset, so like a tiny set within a set, that's a subset of the sample space, which is the big overall set, all the possible outcomes. So an event could be any little subset within the sample space, usually designated by capital letters, so like event A, B, C, just capital letters. And here's the notation we use. Like probability of event A, capital P, parentheses A, so P of A. Probability of A, that's our notation. So example 2 here says, consider the scenario from example 1, so rolling two dice. Let's say event A is going to be, the sum is 5. What's the probability of event A occurring? So the sum is 5. So the question is, how many different ways can we roll and get a sum of 5? And not that you would have to think about these. You could probably come up with it in your head, right? But we could roll a 2 and a 3, a 3 and a 2, or you could get a 1 and a 4, or a 4 and a 1. So that's 4 possible outcomes of the 36, where you could get a sum of 5. So we've got 4 possible outcomes. You go 2, 3, 3, 2, 1, 4, or 4, 1. And none of those are special by any means, so they actually all have the same probability. So each one of those has probability 1 out of 36 of happening. So the probability we get a sum of 5, we'll just add the 4 events. So 1 out of 36 for each one, so that's 4 out of 36. And then one thing I'd like to add here is that I'm going to leave this as a fraction. There's really no need to simplify it or call it a decimal for that matter, because when we're talking about probability, it's actually a lot more valuable when you're looking at these, and it's a lot more descriptive if you just leave it as a fraction that's not simplified. So I just want to add that note here. It's more descriptive. It's more descriptive if the fraction isn't simplified. So don't put in a decimal. Don't call it 1/9. Just leave it like this, because now it's like, oh, you're talking about the 4 outcomes out of the 36 total. So just leave it this way. Okay, on to our basic rules of probability. A lot of these you probably know. In fact, probably at least 3 of the 4 you're good with already. So probability is an event, and we assign it to be a number between 0 and 1. So 0 meaning it never occurs, and 1 meaning it always absolutely occurs. So the notation for this, so for any event A, any possible event you can think of, it's got to be a number between 0 and 1. So we say 0 and 1, the probability of A has to be in between those. Okay, so the second rule here. All possible outcomes together must have probabilities whose sum is exactly 1. So if you think about whatever situation it is for your sample space S, if you add up all the possible outcomes, the sum must be 1. The notation for that, capital S here. S is the sample space, so the probability of S, or the probability of an event in S occurring, has to equal 1. So if you add up all the possible outcomes in the sample space, that probability has to equal 1. The third rule, if all outcomes in the sample space are equally likely to occur, the probability that event A occurs can be found using the formula, and this one's pretty implied, but so probability of A is equal to the number of events that correspond to event A, so the number of events corresponding to event A, and just like you're used to, basic probability divided by the total. So divided by the total number of events, or the total number of outcomes in the sample space S. So total number of outcomes in S. And so we're used to just saying like number of successes divided by the total. Pretty basic rule. You probably knew that one already. And the fourth rule, the probability that an event does not occur is 1 minus the probability the event does occur. So we can kind of backdoor our way into some probability solutions, get some answers. The probability something doesn't happen is 1 minus the probability it does happen. So it's almost like the opposite. Okay, so scrolling down here, the notation for that. So I got capital A, and then I got a C up here, my superscript here. A to the C. That's A complement. So the complement of A. That's the notation. The complement, by the complement, I mean that's the probability that A doesn't occur. So A complement, that's the probability that A doesn't occur. So if we want to find the probability of A complement, so probability of not A, we just do 1 minus the probability of A. So this is what's known as the complement rule. Then our last rule here. If two events have no outcomes in common, so they share no events, no outcomes at all, the probability that one or the other occurs is just the sum of their individual probabilities. So if they have nothing in common, then the probability that either one or the other happens is just the sum of their probabilities. So we say A and B are disjoint. If A and B are disjoint, those are two events. If these two events are disjoint, then the probability of A or B happening is just the probability of A plus the probability of B. For example, if you flip a coin, you can't get heads and tails at the same time. So definitely one or the other has to occur. So if I said, what's the probability you got heads or tails? It would be 0.5 plus 0.5, which would equal 1. So this is the addition rule. We call this the addition rule for mutually exclusive events. And we'll talk about mutually exclusive a little more in just a second. But that means two events that can't occur at the same time. So either one or the other has to happen, but they both can't happen at the same time. All right, on to example 2. Suppose that you'll flip a fair coin, so there's no cheating, it's not weighted or anything. It's 50-50. You're going to flip it 3 times. Describe the probability model for this chance process. Okay, so probability model we talked about before. There's 2 conditions for that. So the first is it has to have a sample space S. And if you're going to flip a coin 3 times, there's actually 8 possible outcomes that can occur. So let's define those. So the sample space S. Let's start with the easy one. You can flip it 3 times and get 3 heads. You can go heads, heads, heads. Or you could go heads, heads, tails, heads, tails, heads, tails, heads, heads, so on and so forth. All the different options. You could even get tails, tails, tails. And so the other piece we need for a probability model is that each one of these has to have a probability between 0 and 1. So actually a valid probability. And they're all equally likely to occur. So whether you get tails, 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 or you go tails, heads, heads, they're all equally likely. So each one has a probability of 1 out of 8, 1/8. So probability model, 2 pieces. Has a sample space, and then each event within the sample space is a valid probability. So part B says use your model from part A to find the probability of getting at least 1 heads. So the probability of at least 1 heads, and there's definitely multiple, right? That's like the sum of, like, you get 1 heads, or you could get 2 heads, or you could get 3 heads. So those are the 3 different ways that you can get at least 1 heads. And then it looks like just getting 1 heads, there's 1, 2, 3 ways that can occur. So that would be 3 out of 8 for that one. And then for 2 heads, 1, 2, 3, same deal. So that'd be 3 out of 8. And then 3 heads, there's only 1 way that can occur. That was the first one. So that would be 1 out of 8. So it looks like the total, 3/8 plus 3/8 plus 1/8, that's 7 out of 8. Okay, so that's good, but there's actually a much easier way to do that. The probability that you get at least 1 heads, the other way would just be to do 1 minus the opposite of that. So 1 minus the probability that you get no heads at all. And we would get the same exact result. It's actually a little bit easier to do it that way. That's the complement rule. So you want to know what the opposite is. The probability you get at least 1 heads, you could just do 1 minus the probability you get no heads at all. And there's only one way that you get no heads at all. That's tails, tails, tails there. So there's only 1 out of 8 for that. So that's just 1 minus 1/8. So that would be 7/8. Okay, so let's talk about mutually exclusive events a little bit more. So we say 2 events A and B are mutually exclusive, or synonym for that we use a lot is disjoint. So I said AKA disjoint. if they have no outcomes in common, and thus they can never occur together. So I always think about timing in this case. So for the notation, we say this occurs if the probability of A and B, so if it's written like this, A and B, that means both at the same time. If they're disjoint, the probability they occur at the same time would have to be 0. So the timing means they can never occur together. So then let's just summarize here. What does it mean to be mutually exclusive? Well, that means either one or the other happens. So either one or the other occurs, but they can never happen at the same time. Let me give you a really basic example of that. Let's say event A is the event that you're under the age of 15. And event B is like you're a senior in high school. So definitely there's no one that's under the age of 15 that's a senior. They can't happen at the same time. Now they definitely happen individually, right? Everyone is under the age of 15 at some point that becomes a senior, but they never happen at the same time. So we could say A and B are definitely disjoint. And don't try to tell me you knew a really smart kid that was a senior at the age of 12, okay? Don't ruin my example right now, all right? This thing on the left here, known as Venn diagrams, hopefully you know that phrase, you've seen these before. We use these a lot in probability. So the sample space here, the yellow rectangle here, that's like all possible events. And then A and B, those are the little subsets inside of it. But you'll notice that A and B have no overlap. So they're split apart. That means they can't occur at the same time. A and B are disjoint events. Like if you look at the diagram below it, you see how they have an overlap. So it looks like sometimes they could occur at the same time. So those wouldn't be disjoint. And an example of events that aren't disjoint, let's say, and this is a really basic one again, event A is, you're a female. Event B is you're a senior. Well, yeah, we absolutely have females that are seniors. There's definitely overlap there. Not all females are seniors, but those are definitely not disjoint events. And so that's like this Venn diagram here. So if they're not mutually exclusive, they have some events in common that occur at the same time. Then you see the overlap. So this would be a representation of two events that are not disjoint. So our final example here about AP scores. It says randomly select a student who took the 2010 AP Statistics exam and record the student's score. Here's the probability model. So on the AP exam you can get a score between 1 and 5, and it looks like a 1 had a much higher probability than a 5. So part A says show that this is a legitimate probability model. So there's two conditions that we're going to prove here that we're going to check. One is that whatever these values are that they gave us, that the probabilities should add up to 1. So you can only get a 1 through 5 on the AP exam, so all these individual probabilities should add up to 1. So that's what we have to check first. So the sum of all the probabilities for the AP exam, you can get a 1, a 2, a 3, a 4, or a 5. So probability you get a 1, probability you get a 2, and so on. We have to check by adding those up, and indeed it equals 1. So that seems pretty trivial, pretty basic, but to check and confirm that this is legitimate, that's what we have to check. And the only thing we have to clarify is that each probability in here is a valid probability. So they're all between 0 and 1, so they're all valid. So each individual probability is between 0 and 1. The sum of all the probabilities add up to 1, so therefore this is a valid probability model. Okay, so you randomly choose a kid that took this exam, and part B says find the probability that the chosen student scored a 3 or better. So scored a 3 or better, that'd be 3, 4, 5. So let's use the correct notation though. Probability you got a 3 or better. Probability of a 3 or better would just be the sum of 3, 4, 5. Those are definitely disjoint events, mutually exclusive, right? You can't get a 3 and a 5. You only get one shot to take that in your life, so you can only get one of these scores. So that's the probability of a 3 plus the probability of a 4 plus the probability of a 5. So that sum, and I'm showing these just to show the work, right? I want to get full credit on the AP exam and on my test, so I'm actually going to illustrate where I got this answer from. Those three probabilities added up, 0.584. So believe me, I really don't enjoy writing on the iPad that much. I wouldn't write this out if I didn't have to, but I want to illustrate my work for full credit. And then the last part here, part C says find the probability that the chosen student didn't get a 1. So you got out of that 1 range. So you could absolutely go the route of just adding up 2, 3, 4, and 5. But it's definitely much more efficient here if you just do 1 minus the probability the kid got a 1. So let's use the complement rule here. Probability you didn't get a 1, that'd just be 1 minus the probability that you got a 1. So it's almost like we look at the opposite way and do 1 minus that. So there's only one case where you got a 1. So if you do 1 minus that, the leftover would be the sum of everything 2, 3, 4, and 5. So 1 minus, the probability you got a 1 was 0.233. So that's 0.767. Probability that the kid didn't get a 1. Got a 2, 3, 4, 5. All right, that's all for these notes. I'll see you in class.